ameno, ameno, lanciremo, dorime.
This week we decided to build upon the negative resistor circuit that we built last week, and we decided to build a current source circuit, and here we have two examples of possible current source schematic layouts to look at.
Pictured here is a floating load converter. It is a floating load because neither end of the load is connected to ground. This circuit would be very simple to build, needing only one resistor and a voltage source to allow for a voltage drop here, which would result in a flow of current across the load. This picture here is a grounded load converter. With this setup, you can connect your load to the ground. This area through here acts as a negative resistor, which we learned about last week. Transforming the voltage source and this resistor, you will get the following circuit. Here is the circuit after the transformation has been done. The negative resistor is in parallel with the voltage source in R1. With the negative resistor, none of the current will flow across it, which will allow all the current to flow over the load, which is what you want in a current source.
The advantage of this circuit is that the current being drawn by the load is now independent of the voltage being drawn by the load. Using LabVIEW with the DAC connection, we are only able to read in voltage measurements across potential. However, we need to be able to measure the current flowing across our load. In LabVIEW, the load is indicated here by the resistance of our load. As you can see, we are inputting into it a current which we get by measuring the voltage drop across a shunt resistor with a value of 51 ohms, which is very minimal to eliminate any reduction in voltage drop. That value is then taken and fed into a XY graph formatter that then displays for us an XY graph that shows how our current is dropping as our resistance increases.
Here's the setup we used in lab. Our breadboard shows our circuit that we built. The power is being supplied by the power source over here. We used 5 volts for our supplier, and the op amp was being supplied by 15 volts. Over here you will see the DAC that we used to measure our voltages across 2 different resistors that we were able to then calculate our currents.
We were able to simulate the behavior of our circuit within PSpice fairly accurately. As you can see, both in PSpice and in our circuit, it is fairly level at around 5 milliamps and then begins to drop off as the resistance hits about 1.2 kilo ohms. This is a result of the circuit starting to become saturated, and at this point the linear behavior that was previously desirable is no longer exhibited.
Here is our results when using a Zener diode. Pictured on the left, you will see that that's when it's placed forward, and on the right is when it's placed backwards. However, with a Zener diode, you want to know the voltage required to allow a current flow, and these graphs are current and resistors. So, to get the voltage, you can take I times R. You will then see that when it's placed backwards, it has a lot higher voltage to allow a current flow compared to when it's placed forward.